Good morning, everyone. Welcome to our presentation on CBSE Class 11 Chemistry. Today, we're going to explore the fascinating world of chemistry tailored for Class 11 students. We'll cover the fundamental concepts, important topics, and tips to help you excel in your studies. I'm excited to take you through this journey. Let's get started. Let's begin by exploring what we mean by average atomic mass. This is essentially the weighted average of all the isotopes of an element, taking into account their natural abundances. It's a key concept because it helps us understand the actual mass of an atom as it exists in nature. Next, we'll look at scientific notation rules. Scientific notation is a powerful tool that allows us to express very large or very small numbers compactly and clearly. It's especially useful in chemistry, where we deal with quantities like atomic masses and concentrations. Remember, the rules involve expressing numbers as a product of a number between 1 and 10 and a power of 10. Moving on, the laws of chemical combination are fundamental to understanding how elements interact. These laws, including the law of conservation of mass, the law of definite proportions, and the law of multiple proportions, govern the way atoms combine to form compounds. They form the backbone of chemical reactions and help us predict the outcomes of chemical processes. Finally, we're covering some basic concepts of chemistry. These lay the groundwork for everything else we'll learn, from atomic structure to chemical bonding. Grasping these core ideas is essential for understanding the more complex topics ahead and seeing how all the pieces fit together in the world of chemistry. Let's start by exploring some basic concepts of chemistry. First, chemistry is all about understanding the composition, structure, and properties of matter. It helps us explain how and why things happen at a molecular level. When we talk about matter, we're referring to anything that has mass and takes up space. Everything around us, air, water, the food we eat, are all forms of matter. One key point is that matter is made up of tiny building blocks called atoms. These atoms combine in various ways to form molecules, which are the smallest units of compounds. Understanding these basic concepts is crucial because they form the foundation for more complex topics we'll explore later. Recognizing how atoms and molecules interact helps us grasp everything from how medicines work to how energy is transferred in chemical reactions. So, as we move forward in this presentation, keep in mind that these fundamental ideas are the building blocks for understanding the fascinating world of chemistry. Sure, here's the word-by-word narrative script for slide 4 of 24. Today, we're going to explore what chemistry really is. Essentially, chemistry is the scientific study of the structure of substances, so how their atoms and molecules are arranged. But it's not just about structure. It also looks at what happens to these substances under different conditions. For example, how do materials change when heated, cooled, or mixed with other substances? These changes are fundamental to understanding chemistry. By studying these processes, we can see how substances interact and transform, which is essential for everything from developing new medicines to creating better materials. So, in essence, chemistry helps us understand the building blocks of everything around us and the changes they undergo. This understanding connects directly to our overall theme of exploring the science that explains our world. Let's take a closer look at molecules. Molecules are the fundamental building blocks of matter, and they consist of two or more atoms bonded together. These bonds can be covalent, where atoms share electrons, or ionic, where electrons are transferred from one atom to another. Understanding molecules is crucial because they determine the properties of materials, from how a substance looks to how it behaves chemically. In the context of our overall presentation, recognizing how molecules form and interact helps us grasp the larger picture of chemical reactions and material design. So, when we talk about molecules, we're really exploring the tiny units that make up everything around us. Let's talk about the meter convention, also known as the Treaty of the Meter. This is an important international treaty that was signed way back in Paris on May 20th, 1875. It was signed by representatives from 17 different nations, including countries like Argentina, Austria-Hungary, Belgium, Brazil, Denmark, France, Germany, Italy, Peru, Portugal, Russia, Spain, Sweden, Norway, Switzerland, the Ottoman Empire, the United States, and Venezuela. The main outcome of this treaty was the creation of the International Bureau of Weights and Measures, or BIPM. This organization is an intergovernmental body that operates under the authority of the General Conference on Weights and Measures, known as CGPM, and is overseen by the International Committee for Weights and Measures, or CIPM. The BIPM plays a crucial role in coordinating international efforts in metrology, which is the science of measurement. It also oversees the development and maintenance of the metric system, ensuring consistency and accuracy across countries. This treaty and the BIPM are fundamental to our global system of measurements, allowing different nations to work together seamlessly in science, industry, and commerce. It's a perfect example of international cooperation that underpins the SI system we rely on today. According to the new convention of 2019, there have been some important updates that are worth noting. These changes were made to improve clarity and consistency across the board. It's essential to understand that these conventions influence how we approach the subject matter and ensure we're all on the same page. As we move forward in this presentation, keep in mind that these standards help us communicate more effectively and professionally. So, let's explore what these new guidelines entail and how they tie into the overall themes we're discussing today. Let's take a closer look at the hierarchy table of the SI system. As you can see, it organizes units based on their scale, from the smallest to the largest. At the core, we have the base units like the meter, kilogram, second, and so on. These are the fundamental building blocks of measurement in the SI system. Above these base units, you'll notice the prefixes. These prefixes, such as milli, centi, kilo, and mega, help us easily scale units up or down by powers of 10. For example, a kilometer is 1,000 meters, and a milligram is 1,000th of a gram. This hierarchical structure is crucial because it provides a consistent and logical way to measure and communicate quantities across different fields and applications. It ensures that everyone understands the scale and magnitude of a measurement, which ties directly into the overall theme of standardization and precision in science and engineering. Understanding this hierarchy helps us appreciate the simplicity and flexibility of the SI system, making it easier to convert between units and maintain accuracy in our work. Let's take a closer look at the density triangle. This concept is really useful for understanding the trade-offs involved in designing materials and structures. The triangle highlights 3 key factors: strength, weight, and density. You can think of these factors as points on the triangle, where improving one often affects the others. For example, increasing strength might mean adding more material, which could increase density and weight. Conversely, reducing weight often involves selecting less dense materials, which might impact strength. The most important takeaway here is recognizing the balance needed among these 3 aspects. When designing, we need to consider the specific requirements of our project, whether we prioritize durability, efficiency, or cost-effectiveness, and then make informed decisions based on this triangle. Overall, the density triangle helps us visualize these relationships and guides us toward optimal material choices, ensuring our designs meet performance goals without unnecessary compromises. Let's now take a closer look at the rules for scientific notation. Scientific notation is a way to write very large or very small numbers in a compact and manageable form. The key idea is to express a number as a product of a number between 1 and 10 and a power of 10. For example, instead of writing 500,000, we write 5 times 10 to the power of 5. One important rule is that the coefficient, the number in front, must always be at least 1, but less than 10. This makes the number easy to compare and work with. Another rule is about the exponent. If the original number is large, the exponent is positive, indicating how many places you move the decimal point to the right. Conversely, for very small numbers, the exponent is negative, showing how many places you move the decimal to the left. These rules help us keep numbers clear, consistent, and easier to manipulate, especially in scientific calculations. They connect directly to our overall theme of simplifying complex data, making it easier to analyze and communicate scientific ideas efficiently. All right, let's talk about scientific notation, which is a really useful way to write very large or very small numbers. The general form is a times 10 to the power of n, where a is a number between 1 and 10, but not including 10 itself, and n is an integer, meaning it can be positive or negative. This notation helps us compare and work with these kinds of numbers more easily, especially in calculations. When you're writing a number in scientific notation, remember that the coefficient, is always between 1 and 10, and the exponent, n, tells you how many places to move the decimal point. If n is positive, it means the number is large, and if n is negative, the number is very small. This standard makes it much simpler to handle very big or tiny numbers in science and engineering. So, keeping these rules in mind will help you write and interpret scientific notation accurately and efficiently. To convert a number into scientific notation, the first step is to identify where the decimal point is and where the non-zero digit appears. This is crucial because the position of the decimal determines how we express the number in a more compact form. Let's look at case 1. Here, we focus on numbers where the non-zero digit appears after the decimal point. For example, if we have 0.0045, we need to find the first non-zero digit, which is 4, and see where it is relative to the decimal point. The goal is to move the decimal point so that only one non-zero digit remains to the left of it. In this case, we move the decimal 3 places to the right to get 4.5. But remember, each movement of the decimal point in this process is reflected in the exponent of 10. Since we're moving the decimal to the right, the exponent will be negative, indicating a small number. So, for 0.0045, the scientific notation becomes 4.5 times 10 to the power of negative 3. This way, we've transformed the number into a neat, standardized format that makes it easier to work with, especially in scientific and mathematical contexts. All right, let's take a closer look at this example. 2301.8 equals 2.3018 times 10 to the power of 3. Now, to convert this number into scientific notation, we need to move the decimal point. In this case, we'll move it 3 digits to the left. To do that accurately, we first count the number of digits we need to shift. Moving the decimal point to the left means we're making the number smaller, and the exponent tells us how many places we've moved it. So, by moving the decimal 3 places to the left, we're essentially rewriting the number as 2.3018 multiplied by 10, raised to the power of 3. This process of moving the decimal point is crucial because it helps us express very large or very small numbers in a more manageable, standardized form, what we know as scientific notation. Remember, the key is to count the number of places you move the decimal point, and this count becomes the exponent on 10. This method ties into the overall theme of understanding how to handle different types of numbers efficiently, especially in scientific and mathematical contexts. All right, let's look at this example. 0.000023. When we write it in scientific notation, it becomes 2.3 times 10 to the power of negative 5. Now, to understand how we arrive at that, we can think about moving the decimal point. In this case, we move it 5 places to the right. To do this correctly, we count the number of digits we move the decimal point across. So, starting from the original number, we move the decimal 5 digits to the right until we're back to a number between 1 and 10. This process is really useful because it helps us convert very small numbers to a more manageable, standardized form, scientific notation, which is especially important when we're dealing with very large or very small quantities in science and engineering. So remember, the key is counting how many places you move the decimal point and adjusting the exponent accordingly. This ensures your number is accurately represented in scientific notation, making calculations and comparisons much easier across the board. All right, let's look at these numbers and practice writing them in scientific notation. The first number is 0.63 times 10 to the power of negative 3. To express this properly in scientific notation, we want a number between 1 and 10 multiplied by a power of 10. So, we move the decimal point one place to the right, making it 6.3, and since we moved it one place to the right, we adjust the exponent accordingly. Because we moved it to the right, the exponent becomes negative, resulting in 6.3 times 10 to the negative 4. Next, we have 33 times 10 to the negative 3. Again, the goal is to have a single digit before the decimal. Here, 33 can be rewritten as 3.3, and since we moved the decimal one place to the left to get from 33 to 3.3, we need to increase the exponent by 1. So, it becomes 3.3 times 10 to the negative 2. Moving on, 71 times 10 to the power of 2. We want a number between 1 and 10, so we move the decimal one place to the left, turning 71 into 7.1. Because we're moving the decimal left, the exponent increases by 1, making it 7.1 times 10 to the 3. The fourth number is 5,400,000. Notice there's no decimal point visible here, so according to our rule, we assume it's at the end of the number. To write this in scientific notation, we move the decimal point 6 places to the left, resulting in 5.4. Since moving the decimal left increases the exponent, we get 5.4 times 10 to the 6. Finally, 0.00006. We want to express this as a number between 1 and 10 multiplied by a power of 10. Moving the decimal 5 places to the right gives us 6, and because we moved it to the right, the exponent becomes negative, so it's 6 times 10 to the negative 5. Understanding how to convert numbers to scientific notation helps us handle very large or very small numbers more easily, which is especially useful in scientific calculations. Now let's take a closer look at these numbers. First, we have 3.3 times 10 to the power of negative 2. This is a way to express a small decimal, specifically 0.033. Moving on, we see 5.4 times 10 to the 6th power, which is a much larger number, over 5 million. Next, there's 6.3 times 10 to the negative 4, or 0.00063. Then 7.1 times 10 to the 3rd, which equals 7,100. And finally, 6 times 10 to the negative 5, or 0.00006. What's important here is understanding how these scientific notation numbers help us efficiently communicate very large or very small values, especially in scientific and engineering contexts. When we look at these figures collectively, they remind us of the importance of precision and clarity, particularly when dealing with solutions or measurements. This slide emphasizes that grasping these notations is crucial for interpreting data accurately, which ties back to our overall goal, ensuring we communicate complex concepts clearly and effectively. Let's now explore the laws of chemical combination, which are fundamental to understanding how elements interact. These laws help us grasp the predictable nature of chemical reactions. First, we have the law of conservation of mass, which states that matter cannot be created or destroyed in a chemical reaction. This means the total mass of reactants equals the total mass of products. Next, there's the law of definite proportions, which tells us that a chemical compound always contains the same elements in the same fixed ratio by mass. This consistency is crucial for understanding chemical formulas. Lastly, the law of multiple proportions explains that when two elements form more than one compound, the ratios of the masses of the second element that combine with a fixed mass of the first are simple whole numbers. Together, these laws provide a strong foundation for studying chemical reactions and compounds, connecting to our overall theme of understanding matter at a molecular level. So, this slide highlights a fundamental principle in chemistry. Matter can neither be created nor destroyed. This idea is central to understanding how chemical reactions work. It was first put forward by Antoine Lavoisier back in 1789, and it really transformed how we think about substances and reactions. The law of conservation of mass tells us that no matter what kind of change occurs, whether it's a physical change or a chemical one, the total mass of the system remains constant. This concept is crucial because it underpins all chemical calculations and reactions, ensuring that we always account for every atom involved. Throughout this presentation, we've been exploring how matter behaves and interacts, and this law is a key piece of that puzzle. It helps us understand that even when atoms rearrange, the overall amount of matter stays the same. This law was given by a French chemist named Joseph Proust. He observed that a given compound always contains exactly the same proportion of elements by weight, regardless of where or how it's made. This is known as the law of definite proportions. Essentially, it means that no matter the source, the ratio of elements in a compound remains constant. This concept is really important because it helps us understand that chemical compounds have a fixed composition, which is a key idea in studying chemistry. It ties into the overall theme of how elements combine in specific ways to form substances with consistent properties. This law was proposed by Dalton in 1803, and it marks a significant step in our understanding of chemical combinations. According to this law, when two elements can form more than one compound, the key idea is that the ratios of the masses of one element that combine with a fixed mass of the other element are always small whole numbers. What this means is that if you take a specific amount of one element, the amount of the other element that combines with it will always be in a simple whole number ratio, like 1 to 2 or 3 to 4. This concept is crucial because it helps us understand the consistent, quantifiable relationships between elements in compounds. It ties into the broader theme of how atoms combine in predictable ways, which was a big step towards the modern atomic theory. So, in essence, Dalton's law of multiple proportions gives us a fundamental rule about the ratios in which elements combine, reinforcing the idea that chemical compounds have definite, simple ratios of elements. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume. This is true as long as all the gases are at the same temperature and pressure. Essentially, Gay-Lussac's law of gaseous volumes tells us that the volumes of gases involved in a reaction relate to each other in whole number ratios under consistent conditions. This insight was important because it helped us understand the quantitative relationships between gases in chemical reactions, which is a key part of the bigger picture of gas laws and chemical stoichiometry. In 1811, Avogadro proposed a really important idea that helps us understand gases better. He suggested that equal volumes of different gases, when measured under the same temperature and pressure, should contain the same number of molecules. This is a key point because it links the volume of a gas directly to the number of molecules it has, provided the conditions are constant. This idea is now known as Avogadro's law, and it's fundamental in chemistry because it helps us compare different gases in a meaningful way. It emphasizes that the quantity of gas molecules is proportional to its volume when temperature and pressure are kept constant. In the broader context of our presentation, Avogadro's law helps us grasp the concept that gases behave in predictable ways, which is essential for understanding gas laws and their applications. It's a cornerstone for developing our understanding of molar relationships and the behavior of gases in various reactions. All right, let's talk about average atomic mass. This concept is really important because it helps us understand the weighted average of all the naturally occurring isotopes of an element. Each isotope has its own mass and abundance, and when we calculate the average, we consider both of these factors. Think of it as a way to find the most representative mass for an element as it appears in nature. This average is what you see on the periodic table, and it's crucial for calculations in chemistry, like molar mass or stoichiometry. So, in essence, the average atomic mass gives us a realistic measure of an element's mass, taking into account the different isotopes that make it up. Many naturally occurring elements exist as more than one isotope, which means they have different versions of the same element with varying numbers of neutrons. When we consider these isotopes and their relative abundance, or percent occurrence, we can actually calculate the average atomic mass of that element. For example, carbon isn't just one single isotope. It has 3 common isotopes, each with its own mass and abundance. By taking into account how much of each isotope is present, we can determine an average atomic mass that reflects the element as it naturally occurs. This concept is really important because it helps us understand why the atomic masses listed on the periodic table are not whole numbers. They're weighted averages based on these isotopic distributions. So, in essence, the average atomic mass gives us a more accurate picture of an element's true mass in nature.